class acceptability part, this part you were able to write. So let's just practice a numerical based on this and move forward to the types of magnetic substances that we have, and then I'll start with the chapter. So the question says a solenoid has a material of relative permeability as 400. So mu R is given as 400. And if the solenoid has 1000 turns per meter, 1000 turns per meter means, class, please open the camera, all of you. Ali, Anisa, Aisha, Ubaidullah. So yes, the solenoid has 1000 turns per meter. 1000 turns per meter means small n. Okay, number of turns per unit length. Remember, capital N was the number of turns, but when you divide it by length, it becomes number of turns per unit length. So this is 1000. It says it carries a current of 2 ampere. I is equal to 2 ampere. That's it. This is what is given to us. It says calculate H, calculate B net, calculate I. Okay. See, since this is a solenoid given, that's a very big hint for us how to proceed further. For H, we already did a formula. If you remember from here, B naught is equal to mu naught into H. Okay, this formula. So how is this formula helpful? See, B naught can, for a solenoid, if this for a solenoid I'm calculating, we know the formula is mu naught N I, right? So mu naught is 4 pi into 10 to the power minus 7. Number of turns are 1000. Current is 2. So this becomes 8 pi into 10 to the power. This is 3 minus 4 Tesla. This is the magnetic field B naught. So when you have to calculate it for the magnetic intensity H, see, from the formula B is equal to mu naught H. B naught is equal to mu naught H. So when you have to calculate it for the value of the H, you can just divide it by the permeability. Okay. Anyways, from here also directly, if you could have written permeability would have been cancelled. Okay, so H is equal to B naught divided by mu naught. That is 8 pi into 10 to the power minus 4 divided by 4 pi into 10 to the power minus 7. So directly you can write, so that from here you directly have the value as 2000. Okay, so 2000 Tesla is the value of the magnetic field. You can directly write it from here like this. If you know the magnetic field, like I know the magnetic field here, mu naught Ni equal to mu naught H. So mu naught gets cancelled. This is equal to Ni. So N is equal to 1000, I is equal to 2. That is directly also 2000 Tesla. Okay. Not Tesla, sorry. This is ampere per meter. The unit is exactly the same as intensity of magnetization, ampere per meter. Okay. That's the first part. Second part says the net magnetic field. See, net magnetic field means magnetic field due to both the medium. So for the next magnetic field, you can use mu R into H. The other magnetic field, you can calculate mu, we write it as mu M into H. So we know the permeability for a different material can be written as permeability multiplied to the relative permeability, right? Relative permeability multiplied to the permeability of air will give us the permeability of that medium. So Bm can be calculated using this. So we can put this as mu naught into mu R into H. So mu naught into H, we already know that's 2000. And what is mu R given? 400. Okay, so H is given as 2000, mu naught you already know, 4 pi into 10 to the power minus 7. So we will be able to get the values of Bm. 4 pi into 10 to the power minus 7. Relative permeability was 400. Yeah, this is 400 into H is equal to 2000. Okay, so that gives us the value of the magnetic field in that particular medium. But that's not the net magnetic field. Remember, when initially we started the class, I told you my net magnetic field is due to internal as well as the external factors. All right. So when we consider that, this will be equal to, this is 32 pi into, this is 5, so 10 to the power minus 2 Tesla. This is the magnetic field. And magnetic field due to air, what did we get? 8 pi into 10 to the power minus 4. 8 pi into 10 to the power minus 4 Tesla. Okay, so the net magnetic field will be the sum of both of these. 32 pi into 10 to the power minus 2 plus 8 pi into 10 to the power minus 4. You can solve this later. Whatever value you will get, that will be the net magnetic field. Okay, how do we get the net magnetic field? Due to internal and external factors. So that's it. Okay, last part is intensity of magnetization. See, you already have the value of net magnetic field. You have the value of H. There was a relationship which we did. B divided by I is equal, B divided by mu naught minus I will give us the value of H. So if I change it here, if I take I over here and H over here from this, basically this is the actual formula from which we have written the formula of H. So what will I be equal to? B by mu naught minus H. Okay. So net magnetic field, here we'll get the third part. B net by mu naught minus H will be equal to I. I think we have the rest of the things. Net magnetic field would be this 32 pi into 10 to the power minus 2 plus 8 pi into 10 to the power minus 4, whatever you will solve through the second part, divided by 4 pi into 10 to the power minus 7 minus 2000 is equal to the intensity of magnetization. Whatever you solve, ampere per meter would be the intensity of magnetization. So this you will be able to solve. Pi will be cancelled. 4 will also be gone. Just the power, the decimals you have to manage. 4, if you take common from here, it will do good. Okay. It will be 8, that will be 2. There won't be anything in the denominator, so that you can solve. Where calculations will not be difficult. Calculations will not come difficult from this chapter, except the comparison one, which we did, the analog one. From there it can come. The analog which we did. So the the axial and the equatorial magnetic dipole, those can have some tricky calculations. Otherwise, the rest of the calculations are very easy. In fact, the next chapter also that we'll do, EMI, calculations are very easy. But before that, tell me this one, have you understood this question? It's a question, I think, from your NCERT. Have you got it? Ali, Anisa, Aisha, Ubaidullah. Ali, it's clear. What about others? What's the query? Yes, Anisa? What have you not understood? What do you want me to repeat? Okay, Aisha got, Anisa got. Ubaidullah, what about you? Okay, class, please start writing. Ubaidullah, you're there?
Yes, ma'am. Understood.
Okay, all right. Please write it, all of you. Last class assignment only Aisha has done. Others, your assignment are pending. And class?
Solving.
No, solving part you can do later. Ubaidullah, you have also given the last assignment. No, I have checked it and reshared it with you. And Aisha, yours also have checked. Aisha and Ubaidullah did the bar magnet assignment. No? So first answer was right. Aisha, your assignment was correct. Ubaidullah, your first question was correct. That when a bar magnet is placed in the external magnetic field, then what happens? Why are the closed loops formed? So because north through south, it travels outside, and then south through north inside. So that's the correct answer. But for the second one, let's just discuss the materials. I hope you have written it till here, all of you.
Yes, ma'am.
Okay. So I'll just discuss the magnetic materials with you. That you have to remember it from your end only. See, when we are talking about the magnetic materials, classification of magnetic materials, three kinds of materials you have: diamagnetic, paramagnetic, ferromagnetic. Diamagnetic means feeble magnetization. Feeble magnetization means weak magnetization is there. Magnetization we have already studied. So they have a very weak magnetization, the diamagnetic substances. Okay, because of this, it is in opposite direction to the magnetic field. The answer to the second question. Okay, Ubaidullah and Aisha will be able to relate this. And in paramagnetic substances, there is same weak magnetization. But in ferromagnetic substances, magnetization is very strong. Then diamagnetic substances, they travel in opposite direction to the magnetic field. Okay, wherever is your magnetic field is there, it will be opposite to it. While paramagnetic will tend to be aligned towards the same direction, and same direction for the ferromagnetic as well. Then they are weakly repelled by the magnet. Wherever the feeble term is there, you just understand it by the term weaker. So they are weakly repelled by the magnets. They are weakly attracted, while the ferromagnetic are strongly attracted by the magnets. And see, this means this. I'll just remove only. They have the tendency to move from stronger regions of magnetic field to weaker regions of magnetic field. Okay, so the diamagnetic substances have the tendency to move from stronger to weaker, while paramagnetic also weaker to stronger, and the same thing is with ferromagnetic. So ferro and para weaker to stronger, while dia is stronger to weaker parts. This means that wherever the strong magnetic fields are existing, from this region it will move to a region where lesser magnetic field is existing. Then some examples are there which you should remember: copper, lead. Just remember one or two. You don't need to remember silver, gold, and all rest of it. Just remember two to three. That's sufficient. Sodium chloride, copper chloride, manganese, chromium, aluminium from the paramagnetic one. And ferromagnetic iron is the most important. Iron has to be mentioned. Cobalt, nickel. Then alloys like alnico, aluminium, nickel, and cobalt. Alloys are also present in the category of ferromagnetic substances. So these differences you'll have to learn and remember. Then there are certain differences based on the relative permeability and the susceptibility. So in case of diamagnetic substances, the susceptibility is very small and it's negative. So its value is very, very less than 1, because it is negative and it's small also. So value is less than 1, very much less than 1. While in paramagnetic substances, it is small but positive. Positive means a little greater than, a little less than 1, not very, very less than 1. While in case of the ferromagnetic substances, the susceptibility is very much greater than 1. If you remember when we did the chapter 4th, before this, I told you that iron and mostly the ferromagnetic substances have the permeability. Like for iron, I told you it is around 1000. We discussed and you have written it in your notes also. Okay, so this is how you can relate it. Coming to this is the relative permeability. It is 1 plus susceptibility. So it is slightly less than 1. Okay, this one. While for paramagnetic, it is slightly greater than 1. For ferromagnetic, it is very much greater than 1. So no need to write it from here. It will just waste your time. I share you in writing in the form of a table. Right now only I'll just forward you on WhatsApp, okay? Or have I shared with you? No. Okay, I'll share it. We'll start with the next chapter that's there in this chapter. And if you have
Ma'am,
any doubt, yeah,
uh, that repulsion was due to opposite movement to magnetic field lines.
opposite movement, yes. Opposite movement to magnetic field line. The opposition was there. Okay. But weaker magnetization is existing. That point you have to mention. And about for diamagnetic, those paired electrons will also have to be mentioned. Okay. Your assignment was correct, Ubedullah. Just one more additional part. Okay. Now, coming to the next chapter. See, the first unit that this is the fourth unit. The first unit that we had was the electrostatics, okay, where your electric charges and potential was there, electric charges and field, then electric potential was there. Then the second unit was current electricity, okay. Third unit was moving charges and magnetism and matter. Unit, not chapters, units I'm telling. This is the fourth unit, and in your fourth unit, mainly you have to do two chapters, EMI and AC. Okay. The chapter sixth, which is present, is electromagnetic induction. It's a very easy chapter. Just practice per day class, that will do good. Okay. I even told you initially that practice the first four chapters in detail. The rest of the chapters will be short and easy. There are majorly four topics in this chapter. Okay. EMI chapter, and chapter 7th is the alternating current. Then you have the last chapter as EM waves. These are there exactly in your NCRT. So we will also be going in the same order of NCRT. I'll just start with electromagnetic induction. So what's new in this chapter that we'll study? Few things are there which we haven't discussed, but just pay attention in the class and practice the assignments, revise the class notes. This chapter will be done very well. Hey, class, when we initially discussed, those who have the cameras closed, please open the cameras, rest of you also. And if you have any doubts in this, please let me know. See, we discussed that initially we saw that when current was there, means charge was at rest in electrostatics. Charges began their motion, current, electricity. But throughout the previous unit, we were just studying the fact that when current is existing, we have magnetism, we have magnetic field. Even at the matter level or at the atomic level, we saw if electrons are evolving, that will give rise to current. So our focus was if current is existing, it gives rise to magnetic field. Current carrying wire, this gives rise to magnetic field. So we saw this is done. Now, electromagnetic induction deals with the reverse. If you have a magnetic field, will it give rise to the current or not? Okay, current carrying wire will definitely give rise to the magnetic field, but will the magnetic field give rise to current? So this was answered by Faraday and his experiments. Answer was yes, magnetic field will also give rise to current. And all the concepts of electromagnetism will be involved. Means electro is for the electric field part, magnetics for the magnetic field part. So electric field, magnetic field, all will be combined. So the entire first book is completely related to what you studied. First topic is very easy, that is magnetic flux. We already discussed electric flux. Electric flux's formula, can anyone tell me? What's the formula of electric flux, which we have done in the first chapter? Yes, formula of electric flux.
Q by epsilon.
E A cos theta, yes. That was Gauss law. Q by epsilon naught, no, which you're saying with you all. That is the Gauss law. That is also the formula, but that is according to Gauss law. If you are not applying the Gauss law, then the formula, as rightly answered by Aisha, that was E dot S. Okay. So magnetic flux is what? Similar to your electric flux as it is. See, if I have multiple magnetic field lines crossing, all these are magnetic field lines, and they're crossing a surface perpendicularly. Like if I have this, many field lines are like this. Lots of field lines at different points, lots of different field lines are moving. Which of them will be perpendicular to the plane? Perpendicular to the plane means if I take this angle, this has to be 90 degree. This will be 90 degree. All these will be perpendicular to the surface. Okay. Then this is what is known as the flux. Now here I'll say if I count, see 1, this is 2, this is 3, this is 4. So I'll say the magnetic flux will be 4. And one more thing, from now onwards, try to differentiate your flux using a subscript of E or B for electric and magnetic. Because when you get your combined questions at the end, you will have electric flux and magnetic flux both. So what is magnetic flux? Number of magnetic field lines perpendicular to the plane surface. That's it. Okay. But see, it's difficult to have the number of field lines always. Like you will be confused if I give you many lines. How will you count? How much can you count? And what if the number of field lines are not given? If the number of magnetic field lines are not given, then how will we solve? So for that purpose, we require a formula. The formula of magnetic flux is similar to the electric flux. You had E dot A there, here it will be B dot A, just as it is. So let's say there's a surface. This is a plane surface class. And in this plane surface, let's say the surface area is S, or you can take it as A. Now, there are certain magnetic field lines which are crossing the surface. Now, pay attention. Here is also one angle that is formed, that the magnetic field forms with the plane sheet. This magnetic field forms with a plane sheet. This is also one angle, but you don't have to consider this one. You will always drop a perpendicular, which is known as the area vector. This will be perpendicular to the surface. You have to drop this first, whether it's any question of magnetic flux. Okay. Then you have to consider the angle between these two. This is the angle which will be considered as theta. Okay, so theta is between B and N cap, not between B and the plane. This we did multiple times in electric flux as well. Now coming to the formula of magnetic flux, very easy. This is B dot S dot product. So definitely the resultant will be a scalar. In class 11th, I think Ali must be remembering it. We did that when you use dot product, then the resultant is always a scalar, whether you are using vectors or anything else. So here also the magnetic flux will be equal to B S cos theta. That's it. Okay, this will be equal to B S cos theta. Now, if we use the SI unit here, SI unit, see, this is given as Weber. So WB is used to represent 5 Weber, 6 Webers, like this Webers is given. And this is exclusively for the magnetic flux. So I'm just quickly repeating. See, it was observed that current carrying wire current used to give rise to magnetism, and that was proven through all the experiments. But then later Faraday did certain experiments to prove whether magnetic field will give rise to current or not. And the experiments also I'll tell you in today's class itself. So answer was yes. And then there is a concept of magnetic flux, which you should know because that will be related to the entire Faraday's experiment. So magnetic flux basically says that the number of field lines that are perpendicular to the plane surface. So you count the number of field lines, those number of magnetic field lines are the magnetic, is known as the magnetic flux. If I have electric field lines, that becomes the electric flux. Magnetic field lines, magnetic flux. Formula is simply B dot S, that is Bs cos theta. Angle is always taken between the magnetic field and the perpendicular, that is the area vector. It's a scalar quantity and the unit is Weber. Till here, am I clear to all?
Yes,
All right. Okay, then please copy it till here. We'll practice some numericals and then we'll do the Faraday's laws. Okay.
We are doing sixth chapter, right?
Yes, yes, electromagnetic induction, EMI. We are doing sixth one. Yes, just write it in one line just so that you don't get confused because many students in other batches were getting confused about the units and all. So that's why I just clarified with because AC and EMI and especially EM waves and all. So just write it one line. If you want, you can avoid it.
Yes, ma'am.
Okay. Let's practice one or two numericals. See, this says magnetic field of 2 Tesla exists in space. It is inclined at 30 degree with the plane. It says you have to calculate the magnetic flux through it if the area is given as 10 meters square. The magnetic field is given as 2 Tesla. Then uh, it says area is given as 10 meters square. Can anyone tell me what is the angle which I should put? What's the angle given? What do you think should come? Correct, Ali. Very good. 60 degree. See, 30 degree. This is the magnetic field. This is the plane. So 30 degrees made with the plane. I told you, you never take this angle. You drop a perpendicular, which is known as the area vector, and you consider this angle theta, which is 60 degree. 90 minus 30 is 60. Now you solve rest of the question. Magnetic flux is equal to B dot A, which is equal to B A cos theta. B is 2, A is 10. This becomes cos 60 degree, that is half. So answer is 10 Weber. Okay, write down this question. We'll practice one more question. Done.
Last done.
Okay. Let's see this question. This says magnetic field is given as 10 I cap plus 3 J cap plus K cap Tesla. This exists in space. We have to calculate the flux through an area of 2 meters square in YZ plane. The magnetic field is given as 10 I cap plus 3 J cap plus K cap. And regarding the area vector, it's given 2 meters square in YZ plane. Means it has not specified the unit vector. So for area, we already discussed that we have to choose an area vector. So can anyone tell me what will be the area vector for YZ plane? Area vector for YZ plane means for YZ plane, which will be the perpendicular axis. No, Aisha. YZ is the plane. C class. YZ is already the plane. This is the YZ plane. See, this is the XY plane. This is the YZ plane. This is the XZ plane. So if I have the XY plane, YZ plane, see Y axis and uh, Z axis. Perpendicular to it, when I choose the area vector, where will it point? Which axis is this if I take this? Hmm? X-axis. Very good, Ali. This will be X-axis, which is I cap. So now you can solve. The magnetic flux will be B dot A. So it will be 10 I cap plus 3 J cap plus K cap dot 2 I cap. So this is equal to 20. 10 into 2 is 20. 3 into 0 is 0. 1 into 0 is 0. So 20 Weber. Is it clear to all this question? Magnetic flux is clear, this whole topic. Okay, except Ali and Aisha. Anisa, you getting Ubaidullah?
Area
Area vector. Oh. See, you have the YZ plane. Okay, you have to choose an area vector, means you have to drop a perpendicular to this. So if this is my y-axis, this outer one is the z-axis. So definitely the area vector is pointing towards the x-axis. For x-axis, we use I cap. Okay. If it was, let's say, xy, so perpendicular to xy is the z-axis, so we would have written k cap. If it was xz, so perpendicular to the xz is the y, we would have written j cap. So since this is yz, perpendicular to it is the x-axis. Got it?
yes, ma'am.
All right, please write it, then we'll move on to the Faraday's laws of EMI. Are you done?
Do
Now completed, Ubedullah?
diagram.
Okay, moving to the Faraday's experiment. So the first experiment that we have is what he did, just pay attention to the experiment. He just took wire and turned it in the form of a coil. And then what did he do? He connected to this coil a galvanometer. Now, what's a moving galvanometer? We've already studied its principle and everything. You already know by now. So, see here. Then he took a bar magnet, north polarity, south polarity, and he moved this bar magnet closer. So, closer to this coil. So, what was observed? Basically, it was seen that when the bar magnet was brought closer to the coil, it was seen that the magnetic field lines emerged. Because obviously bar magnet is coming closer to a coil, so magnetic field will be there. So definitely magnetic field lines were there. But that's not the main point, because if bar magnet is there, it will cause magnetic field line. That's not a new thing. But the new thing was that this galvanometer showed a deflection. Now we have studied that galvanometers do not show deflection due to magnetic field first, unless there's a current in the circuit, right? That's the function of a galvanometer. We discussed even that moving coil galvanometer has just a function to tell you whether the current exists or not. Yes or no. So if the galvanometer is moving, it means definitely there is a current in your circuit. So when the bar magnet is coming near to the coil, magnetic field was there. Due to bar magnet coming near the coil, there was a deflection. So isn't it reverse to what we've already studied? Now this time the magnetic field is causing the current to come. So galvanometer showed a deflection in the circuit that showed a current is existing. Got it?
Yes, ma'am.
Okay. In the next experiment, what did he do? He took the same coil, connected it to a galvanometer. See, there is no battery connected. There is no battery put. He took a bar magnet again, North Pole, South Pole. But this time, instead of moving the bar magnet, he moved the coil near. It's a confirmatory experiment. That is it the bar magnet only, or there is the relative movement of the coil with respect to something or the other? When the coil, see in this case, coil is moving. Okay, in this case, the bar magnet is not moving, coil was moving. Again, it was observed that the galvanometer showed a deflection because when the coil went near the bar magnet, again magnetic field was there and magnetic field was causing the current. So, see, this current that you get, now one thing I'll just tell you here itself before I forget, this current is not the real current that comes through the battery. It wasn't at the first place. Like if I didn't have this bar magnet, I wouldn't have got any magnetic, I wouldn't have got any current. One current is when you set up a battery, when you set up a circuit, the charges are released from the battery and the current is flown. That is one major, what do we say, the current that we actual literal current that we have, which we've already studied in chapter 3, current electricity. Now, which current is this? This current wasn't there. Because of magnetic field, a current has been induced in our circuit. So this current that is induced in your circuit is known as the induced current. You will often use this term, induced current and induced EMF. We'll use these terms often, induced current and induced EMF. Because of the bar magnet, there was a current coming, which was the induced current. Similarly, an EMF was induced in the coil. Induced means induction. Remember the properties of charges that we did, the methods of charging, charging by friction, charging by conduction, charging by induction. So the charges are induced. They are not present at the first place. They are being induced because of the bar magnet's existence. Okay, last experiment was done. He took a soft iron rod, and on this iron rod, he wrapped wires and connected it to a galvanometer and connected it to a battery this time, connected to a key rheostat. See, current was observed, but because of all these things, no variable resistance and all, the current that you obtain is the alternating current. So, no need to do it in this chapter. Just draw it, have it in your notes. When we'll do AC, then this will be clear. Okay, so see, what can I conclude from all the experiments? Like whatever he did, we can conclude one fact that whenever magnetic field was there in a coil, current is being induced. More or less, we can say EMF is being induced. Can we say? And why is it being induced? We can simply say magnetic field is changing. This magnetic field is changing, which wasn't there. This magnetic field is changing. Magnetic field will cause the flux to change. And all these things are leading to what? Induced EMF or induced current in your circuit. V is equal to IR. Using Ohm's law, you get either of them, you will have both induced current and induced EMF. This is what I can conclude. So what are the conclusions from the Faraday's experiment? See, he said that whenever the magnetic flux linked with a closed circuit changes, magnetic flux changes. Why? Because magnetic field is changing. So an induced EMF and hence an induced current is set up in this coil. That was concluded. Yes, that we could also observe that yes, magnetic field is changing, current will be induced, and so does the EMF. Second is higher the rate of magnetic flux within the closed circuit, greater is the induced EMF of current. Basically, this tells us the fact that rate of magnetic flux is what? Magnetic flux changes with respect to time. So EMF is directly proportional to this rate of change of magnetic flux. Okay. If the magnetic flux is changing with a very great rate, okay, then the EMF will also be produced at a very higher rate. And if the rate is very slower, then the EMF will also be very slow. So what can we conclude from the Faraday's law? First, the conclusion point that whenever the magnetic field changes, magnetic flux changes, induced EMF is there. But then what about the formula part? We can say this induced EMF is directly proportional to rate of change of flux. Means if I say If I say rate of flux or change in flux means d phi or delta phi. This means the change in flux. Rate means with respect to time. So we can say EMF is directly proportional to rate of flux. EMF is directly proportional to rate of change of flux. Now this elaboration I'll do next, but first you write it till here, this point, that whenever magnetic flux linked with a coil changes, EMF is induced. This is the first law of Faraday. Second is width is directly proportional to rate of change of magnetic flux. This whole experiment and the conclusions, are they clear to all of you?
Yes, ma'am.
Okay. Start writing. If you stuck anywhere, please let me know. I'll discuss. Okay. Please start writing. Aisha, the third one you say? That you can say because alternating current is there. So alternating current we haven't done. I'll tell you in that chapter.
First point I'm not able to understand.
First point says whenever the magnetic flux linked with a closed circuit. This means through a coil. Closed circuit means your coil circuit that we did in the experiment. Whenever flux is changing, means see, due to magnetic field, flux will also change because flux is equal to BA cos theta. So if magnetic field is changing, the flux will also change. So when this happens, then there is an induced EMF. According to his experiments that was observed, that galvanometer moved the coil. So induced EMF and induced current were observed. That's what's written. Whenever the magnetic flux linked with the closed circuit changes, an induced EMF and hence an induced current is set up in it. Uh, is the confusion clear now?
Yes, ma'am.